Hi, back again with some more high level, simple perspective on artificial intelligence, AI. Last time I said that AI is at its heart a model that relates inputs to outputs based on what it has learned and the statistical patterns it has gleaned through that learning. Today, I hope to give a little high level intuition again about how that learning part takes place. Again, mostly aimed for those of you who are curious but not super familiar yet with the inner workings of AI models. Now, these models learn by using lots and lots of good training data, which is usually just examples gathered from the real world, such as sentences that have been written on the web in books, etc., pictures that have been taken, music that has been performed, and so on. Now, as you can imagine, there may be some sticky copyright issues regarding some of that data that's used, which I may talk about in a future video. Anyway, these real-world samples are turned into numbers. They're numerically encoded in some way so that the model can deal with them. For a simple example, words in a sentence might each be turned into a number, representing the order that word appears in a set dictionary. Those digitized inputs then from the training data are fed into the model, and the model makes a prediction of the output, as we talked about last time. Now, when the model hasn't yet been trained or not trained very much, those outputs are going to be pretty random and likely far off the mark, naturally enough, if it doesn't have any learning yet to base the output on. Now, the learning part takes place like this. During training, the model compares its predicted output with what the training data says the output should have been, i.e., what was observed in real life. That training data actual output is commonly called a label in the AI world. And I understand that label is maybe not the most intuitive word, but that's what's used. Now, the difference between the predicted output from the model and the actual output that was expected, and remember that everything's been turned into numbers, is then used to tweak a whole bunch of internal variables in the model called weights or parameters. Now, those weights are where the statistical patterns relating inputs to outputs are captured. That's where they are learned and remembered. In the big models we see today, there are lots of those internal weights, almost unimaginable numbers. So the sophistication of those patterns that they can learn is very high. They're so huge and so sophisticated, it can be really hard sometimes to get our heads around it, to be perfectly frank. So those weights are tweaked such that what the model would have predicted is closer to the actual output from the training data. It doesn't just set the weights to predict the actual output. It nudges them in the direction of the actual output. Now, this nudging approach is a key part of the secret sauce of machine learning and why these models are good at squishy things. If we simply set the model weights to predict the actual output from the training data every time, the weights would just bounce around with each new piece of training data without any memory, so to speak, of the previous training data, and they'd only ever reflect the last piece of data that was encountered. Now, I'm sure we all know some people who operate like that, but the nudging is where the learning comes in, and it ensures the model continually gets better and better at predicting the intended outputs across a wide range of training data. Now, having grown up as a rancher, I kind of imagine this nudging process as a way of learning to be like herding cattle. Now, the training data does need to exhibit general consistency. Inconsistent training data will lead to inconsistent results and a model that just wanders around without getting anywhere, without learning. So you can see that to achieve good learning, we have to feed lots of data, good data, into the model, and sometimes the same data over and over again to help reinforce the patterns that can be learned from that piece of data. This improves the model's predictive accuracy, of course, and it also allows it to handle that wide range of inputs and predict a range of outputs. And once the training is done, you use the model by sending in inputs, and then the model predicts an output, which you can use for some purpose. And that output should be consistent with everything it has learned previously, if it's been trained properly, even if the particular set of inputs that were just sent in have never been seen before. And that's where these models start to feel a little bit magical. It feels like, oh, it figured that out. but it's just using the statistical patterns. Often the training of the model continues as it's being used. So every time a model gets feedback on whether it hit the mark with its prediction or not, it gets a thumbs up or a thumbs down, for example, it uses that feedback to continue to tweak those internal weights and get better and better. Many thanks. That's my thought for now. I'll be back soon with more. Take care.